Our story begins in violence. 4.5 billion years ago, our Earth was not a blue marble, but a roiling, screaming sphere of molten rock and toxic gas. This was the Hadean Eon, an age appropriately named after the underworld. It was a planet-sized furnace, shrouded in a choking atmosphere, utterly incompatible with life as we know it. For hundreds of millions of years, this was the state of our world. A sterile, hellish forge. Even as the surface began to cool and crust over, peace was not an option. Our young solar system was a chaotic shooting gallery, and Earth was its prime target. This era, known as the Late Heavy Bombardment, was a relentless assault of celestial fire. Asteroids, some the size of entire continents, struck the planet one after another, their impacts powerful enough to boil the fledgling oceans and vaporize any crust that had dared to form. Any corner of the planet that might have been experimenting with chemistry was repeatedly and violently sterilized. This cosmic cataclysm finally subsided around 3.9 billion years ago. For the first time, the Earth was relatively stable. The surface was cool enough for liquid water to remain, and the planet finally had a moment of quiet. Logic would suggest that from this point it would take an immense span of time, perhaps a billion years or two, for the slow, random dance of chemistry to stumble upon the miracle of life. But the rock record tells us a profoundly different story. The very oldest fossils we have, ancient microbial mats called stromatolites, are etched into stone from 3.7, perhaps even 3.5 billion years ago. This is not a slow, patient process. This is a planetary-scale sprint. The moment the Earth became even remotely habitable, life was already here, thriving and building empires. Let's truly grasp what this timeline implies. The window of opportunity, from a safe planet to a living one, may be as short as 200 million years. In the grand scheme of cosmic time, this is the blink of an eye. This is the central problem, the statistical miracle that keeps biologists and chemists awake at night. It's not that life emerged. It's that it emerged, seemingly instantly. Because the leap from non-life to life is not a small step. It is the most profound and complex transition we have ever encountered. We're not just talking about a puddle of chemicals. We are talking about the spontaneous creation of an information system. Life requires a molecule, something like RNA or DNA, that can not only build machinery but, crucially, store a blueprint and copy itself. This is the difference between a random pile of bricks and a self-constructing, self-replicating factory. The classic explanation, which we all learned in school, is the primordial soup. It's a beautiful idea, first proposed by Charles Darwin as a warm little pond. In the 1950s, the Miller-Urey experiment famously tested this. They took a flask containing the simple gases of the early Earth, methane, ammonia, water, and zapped it with an electric spark to simulate lightning. The result was revolutionary. After just a week, the water turned a thick, brown red, rich with amino acids. These are the fundamental building blocks of proteins, the nuts and bolts of living cells. The experiment was a staggering success. It proved that the ingredients for life could be assembled naturally, right here on Earth, from simple, non-living materials. But here is the critical and often overlooked gap in that story. They made amino acids. They made the bricks. They did not, however, make the blueprint. They didn't make a self-replicating molecule. They created no code, no information, no DNA. Making a random amino acid is child's play compared to the unfathomable complexity of spontaneously assembling a strand of RNA long enough and stable enough to carry instructions and copy itself. The astronomer Fred Hoyle famously and dismissively captured this statistical hurdle. He said the odds of life emerging randomly from a primordial soup were the same as the odds of a tornado sweeping through a junkyard and assembling a Boeing 747. Now, to be fair, chemistry is not entirely random. Certain molecules fit together better than others. But the analogy, while dramatic, drives home the sheer scale of the improbability. We are left with a fundamental contradiction. We have a puzzle of almost infinite complexity, the spontaneous creation of a genetic code, and we have an impossibly short ticking clock in which to solve it. Nature had to go from a sterile, battered rock, still glowing from its bombardment, to a planet teeming with replicating microbes in a geological instant. This timeline just feels wrong. Feels too short, too easy, for the hardest problem in the universe. So what if our premise is flawed? What if we've been searching for the answer in the wrong place? What if the clock didn't start on Earth at all? What if life's code was already written billions of years before the Earth even formed, and was just delivered? If life's components weren't forged here, in that impossibly short window, then they must have come from somewhere else. They must have been delivered. The delivery system, ironically, would be the very asteroids and comets that were once our planet's greatest threat. But how could we possibly know? We can't rewind time. We must, instead, look for the packages that are still arriving today, the messengers from the void that survived their fiery descent. We call them meteorites. Most are just chunks of iron and rock, fragments of failed planets. But a rare and precious few are something else entirely. They are known as carbonaceous chondrites, and they are, without exaggeration, the most important rocks on Earth. They are not just rocks. They are time capsules. They are pristine, untouched samples of the original dust and gas from which our sun and every planet were born, over 4.5 billion years ago. On the morning of September 28, 1969, a quiet Sunday in the small town of Murchison, Australia, the sky was torn open. A brilliant fireball, bright as the sun, exploded with a deafening sonic boom. It rained down over a 5-square-mile area, scattering thousands of small, dark, and strangely light stones. Residents who picked them up noted a peculiar, sharp smell, like tar or alcohol. They had no idea they were holding the most significant extraterrestrial object ever recovered. The Murchison meteorite, as it came to be known, was rushed to laboratories, which were eagerly awaiting samples from the upcoming Apollo moon missions. Scientists were prepared for pristine analysis, and what they found inside was staggering. The rock was packed with organic material. First, they found water, locked inside its clay structure. Then, they found simple organic compounds, the same ones that smelled like tar. But then, they found the real treasure. Inside this single, sterile rock from the asteroid belt, they identified over 70 different types of amino acids. This was a revelation. The Miller-Urey experiment had shown that these building blocks could be made on Earth. Murchison proved, unequivocally, that they were also being made in deep space, long before Earth itself had even finished forming. This alone was a paradigm shift. But amino acids, as we've established, are just the bricks. They don't make a blueprint. They don't carry information. For that, you need something far more complex, a set of molecules known as nucleobases. You probably know them by their letters A, G, C, and T. They are the rungs on the ladder of DNA. Finding amino acids in a meteorite is amazing. Finding the letters of the genetic code itself would be revolutionary. For decades, scientists debated whether the nucleobases they found in Murchison were real, or just contamination from the Australian soil. But in 2011, using state-of-the-art technology, a team of NASA scientists confirmed the undeniable. Inside the stone were adenine and guanine, 2 of the 4 primary letters of our DNA. And, as if that weren't enough, they also found uracil, the key letter that replaces thymine in RNA, the molecule many believe was the precursor to all life. This is the smoking gun. But it immediately raises a critical question. How did they know? How could they be certain these molecules weren't contamination from the first microbe that landed on the rock after it fell? The answer lies in a brilliant piece of chemical forensics. It's all about an atom's weight, or what scientists call its isotope ratio. Think of it like a chemical fingerprint. Carbon, the backbone of life, comes in 2 main stable forms. A common, lighter version called carbon-12, and a slightly heavier, rarer version called carbon-13. Life on Earth is lazy. It finds it easier to process the lighter carbon-12. Therefore, almost everything alive on our planet, from bacteria to you and me, has a distinct fingerprint, a specific ratio of heavy to light carbon. It's a signature that screams, made on Earth. The molecules inside the Murchison meteorite did not have this fingerprint. They were found to be rich in the heavier carbon-13, in a ratio that is impossible for terrestrial biology. They could not, under any circumstances, have come from Earth. Their atomic signature proved, beyond any doubt, that they were forged in the cold, uncaring vacuum of interstellar space, long before our world existed. Let that sink in. The fundamental letters of our genetic alphabet, the G and A, that form the instructions for your eyes, your heart, your very consciousness, are not exclusively terrestrial. They exist, fully formed, inside rocks that fall from the sky. This discovery fundamentally changes our understanding of the primordial soup. It wasn't just a warm little pond here on Earth, desperately trying to cook up life from scratch in a few million years. The soup was the entire early solar system. It was a vast, cosmic-scale chemical kitchen, simmering for billions of years before Earth was born. The ingredients weren't just available, they were abundant. And so, as the late heavy bombardment pummeled the young Earth, it wasn't just a sterile, destructive rain. It was a delivery mechanism. For every asteroid that boiled an ocean, countless smaller comets and carbon-rich meteorites, just like Murchison, dissolved into the water. They were, in effect, seeding the entire planet with a prepackaged, concentrated starter kit for life. And perhaps the most profound part of this entire discovery is not just that some organic molecules exist in space. It's that the specific molecules found in these meteorites are the very ones life chose to use. Life on Earth is built from a select menu of 20 amino acids, and the most common ones found in Murchison are the exact same ones at the top of life's menu. This is not a coincidence. This is a clue. This rock, this smoking gun, proved that the alphabet of our existence is extraterrestrial. It is cosmic. But this just deepens the mystery and pushes the question back one crucial step. If the letters of our DNA were written before the Earth, where was the factory that made them? And what else was made there? The Murchison meteorite gave us the letters, proved the alphabet of life is extraterrestrial. But this discovery, as profound as it is, only pushes the question back. How did those molecules get into that rock? To find the answer, we must zoom out, past our sun, into the seemingly empty, black voids of the Milky Way. These are not empty spaces. They are the true factories of creation, the great interstellar molecular clouds. When we look at the night sky, we see points of light, but astronomers using radio telescopes see the shadows. These shadows are vast, dark nebulae, clouds of dust and gas so large they could swallow thousands of solar systems. They are unimaginably cold, hovering just degrees above absolute zero. To our eyes, they are patches of nothingness, like the Horsehead Nebula. But in reality, they are the most fertile places in the entire galaxy, the cold, dark wombs where stars are born. These clouds are reservoirs of the raw elements of existence, blasted across the galaxy by long-dead stars. Trillions of tons of hydrogen, carbon, nitrogen, and oxygen drift in the dark. These are the fundamental atoms of life, the C, H, N, and O that form the backbone of every molecule within us. But in this diffuse, frigid state, they are too far apart to interact. For chemistry to happen, they need a place to gather, a microscopic workbench. The workbench is a simple grain of cosmic dust, no larger than a particle of smoke. These grains, themselves made of silicates and carbon, are the seeds of planets. In the deep cold of the cloud, simple molecules like water and ammonia freeze onto their surfaces. They form a frosty, icy mantle. This ice is the trap. It acts like molecular flypaper, catching drifting atoms, holding them close in a concentrated layer. Now we have ingredients frozen together on a workbench. But a chemical reaction needs a spark. That spark, ironically, comes from the light of nearby newborn stars. Young, hot stars, burning on the edges of these dark clouds, flood the region with intense, high-energy ultraviolet radiation. This UV light is a cosmic forge, penetrating the cloud and striking the icy mantles of the dust grains. This radiation is not a gentle warmth. It is a violent catalyst. The UV photons shatter the chemical bonds of the simple ice molecules, breaking apart the water and ammonia. This creates highly reactive fragments called radicals. These fragments, now energized and trapped together, desperately seek stability. They recombine in new and complex ways, building longer and more interesting chains, one atom at a time. This is astrochemistry in action. And what are they building? At first, simple things like methanol. But as the process continues over millions of years, the complexity grows. We've pointed our radio telescopes like the ALMA Observatory deep into these clouds. We've detected the chemical signatures of glycine, the simplest amino acid. We have found precursors to sugars, like glycolaldehyde, and strong evidence for ribose, the R in RNA. And we've found the unmistakable fingerprints of the nucleobases themselves. This is the critical link. These molecular clouds are not static. They are star nurseries. Eventually, a part of this cloud, enriched with these complex organic molecules, will collapse under its own gravity. It will flatten into a disk. At its center, a new star, our sun, will ignite. The remaining dust and ice, the very same grains that served as workbenches, will begin to clump together. In the cold outer regions of this new system, these enriched ice-coated grains will form comets. In the warmer inner regions, they will form asteroids, trapping these organic compounds inside. The Murchison meteorite was a fragment of one of these ancient, original bodies. It was a fossil from the birth of our solar system, carrying a pristine sample of the products from that interstellar factory. It wasn't just a rock. It was a sealed package of prebiotic chemicals. This isn't a bold hypothesis. It is a direct observation. Using our telescopes, we are watching this process unfold, right now, in star-forming regions like the Orion Nebula. The primordial soup on Earth didn't have to start from scratch. It was given an extraordinary head start. The planet was seeded for billions of years before it even existed. This changes everything. The universe is not a sterile, dead place that life must struggle to overcome. The universe is a chemical factory, and the creation of complex organic molecules appears to be an inevitable byproduct of star formation. The specific molecules of life, amino acids, sugars, the letters of our DNA, are not a 1 in a billion miracle. They are common. The cosmos, it seems, has been busy making a starter kit on a galactic scale. It packs these ingredients into comets and asteroids, delivering them to any new, watery world that forms. We have found the letters. We have found the factory where the ink is made. But a box of letters is not a book. An alphabet is not a language. A starter kit is not life. This still leaves us with the problem of assembly, the miracle of that first replicating molecule. But what if we've been underestimating the universe's delivery service? What if the delivery wasn't just the ingredients? What if it was the recipe itself already assembled? What if the package wasn't just the code, but the machine? What if it was life itself? We have found the letters of our code floating in space. We have found the cosmic factories that build them. This proves the universe is biased toward creating the ingredients for life. But this still leaves us with the hardest problem: assembly. How do you get those letters to randomly arrange themselves into a self-replicating, information-rich strand of DNA? What if they didn't? What if the universe's delivery service wasn't just shipping the parts, but the finished, working machine? This is the bold hypothesis known as panspermia. The word literally means seeds everywhere. It is the ancient and profound idea that life did not begin on Earth. It suggests that life is a cosmic phenomenon, an interstellar infection, and that Earth was just a sterile, fertile incubator waiting to be seeded. This sounds like pure science fiction. But in the last few decades, a more specific, testable version of this idea has emerged: lithopanspermia. Lithopanspermia is the theory that life can be transported between planets, shielded inside rocks. Not as delicate spores drifting on solar winds, but as hardy, microbial stowaways, hitching a ride on planetary fragments blasted into space by asteroid impacts. For this to be even remotely plausible, we would need to prove three things. 1, that a rock can even travel from one planet to another. 2, that any life inside could survive the journey. And 3, that it could survive the fiery impact of arrival. Let's start with the journey. Is there a highway between the planets? The answer is an unequivocal yes. We know this because we have the travelers right here on Earth. In the frozen wastes of Antarctica, scientists have found dozens of meteorites. When they analyzed their chemical composition and the gases trapped inside, they found a perfect match. Not for Earth, not for any asteroid, but for the atmosphere of Mars as measured by our Viking landers. The most famous of these is Allen Hills 84001. It is a 4-pound chunk of igneous rock that was forged on Mars 4 billion years ago, blasted into space by an impact 16 million years ago, and finally landed on Earth 13,000 years ago. This single rock proves, beyond any doubt, that a natural exchange of material between Earth and Mars is not just possible, but has happened. The delivery service is real. But this just brings us to the second, harder question. Could anything survive that journey? The trip would mean millions of years in the hard vacuum of space, exposed to lethal cold and, most importantly, a relentless bath of sterilizing cosmic radiation. For a long time, we assumed nothing could. But our own planet has shown us that our definition of life has been far too narrow. We have discovered a class of organisms that mock our assumptions. The extremophiles. The most famous of these is the tardigrade, or water bear. It is a microscopic, 8-legged animal that is virtually indestructible. You can boil it, freeze it solid, crush it under pressure that would flatten a submarine, and dehydrate it for decades. Most incredibly, tardigrades have been taken into space, exposed to the raw vacuum and solar radiation, and returned to Earth where they were simply given a drop of water and walked away. The tardigrade is a complex animal, a biological tank. But the real champions of survival are far simpler and far more relevant to our story. They are microbes. Meet Deinococcus radiodurans. It is a bacterium with a superpower that borders on magic. Its name means terrible berry that withstands radiation. It can survive a dose of 5,000 grays of radiation with no loss of viability. For context, a dose of just 10 grays is lethal to a human being. What's truly astonishing is how it survives. The radiation does shatter its DNA, just as it would ours. But where our cells would give up, Deinococcus simply begins a repair process. It gathers up the broken fragments of its genetic code and, within hours, meticulously stitches its entire genome back together, good as new. It doesn't just shield its DNA, it rebuilds it. This is a life form that has evolved to endure the very conditions of interstellar space. Now, let's combine these facts. We have proven that rocks are exchanged between planets. We have proven that microbes exist which can survive vacuum and rebuild their DNA after extreme radiation, especially when shielded by just a few meters of rock. The journey is not just possible. It is plausible. So, let's paint a scenario. Let's look at our neighbor, Mars. Today, Mars is a cold, dead, irradiated desert. But 3.9 billion years ago, when Earth was still a molten hellscape, Mars was a different world. It was warmer. It had a thick atmosphere, clouds, and, we are almost certain, vast, stable oceans of liquid water. Critically, Mars was habitable before Earth was. It had a head start. What if life, that statistical miracle, happened there first? Imagine. A microbe, something like Deinococcus, thrives in an ancient Martian ocean. A massive asteroid strikes the planet, just as they did on Earth. The impact launches billions of tons of rock into space, some of which contain colonies of these dormant microbes, flash-frozen and protected deep inside the stone. For millions of years, these rocks tumble through the void, a fleet of tiny, natural arcs. Eventually, one of these rocks, by pure chance, has its orbit intersect with a new, younger, and finally habitable planet. It streaks through the sky as a fireball. The outer layers of the rock are vaporized, creating a heat shield that protects the core. It splashes into a warm, sterile, chemical-rich ocean on Earth, cracks open, and releases its cargo. It would not be an invasion. It would be a seeding. This is the hypothesis of lithopanspermia. It solves our impossible timeline from point one, not by speeding up chemistry, but by giving life a different, older starting line. It suggests that all life on Earth, from the simplest algae to you and me, is descended from that first, successful Martian immigrant. It suggests that we are, in the most literal sense, the aliens. It is a story so powerful, so elegant, it feels like it must be true. The idea that we are Martians, that life was a seed planted in Earth's fertile soil, rescued from a dying, older world, solves our biggest problem. It neatly sidesteps the impossible timeline. It gives life the billions of years it seems to need, just on a different stage. It's a cinematic, epic narrative of survival. And that is precisely why we must be skeptical. A good investigation, like good science, cannot fall in love with its own hypothesis. It must attack it relentlessly with the cold, hard tools of doubt. This grand idea of lithopanspermia, life from the rocks, rests on a chain of ifs, each one a desperate battle against staggering odds. We must, in all intellectual honesty, pour cold water on this beautiful idea and see if it can withstand the chill. Let's first reconsider the journey. We've celebrated the hardiness of microbes like Deinococcus radiodurans, a true Conan the bacterium. But the journey from Mars to Earth is not a quick hop. We're talking about millions of years adrift in the void. For that entire time, the rock is being saturated by galactic cosmic rays, high-energy particles that shred DNA. To be truly shielded, a microbe would need to be at the core of a rock several meters thick. This dramatically narrows the field of viable arcs. Even before the journey, there is the ejection. How does the rock leave Mars? It must be blasted off by a colossal asteroid impact. The sheer, instantaneous violence of this event is almost unimaginable. The shockwave and g-forces from such an impact would be enough to pulverize solid rock, and by extension any microbe inside. It is a profound question whether any organism, no matter how extreme, could survive the very event that sets it free. And then, after millions of years of radiation, there is the arrival. The rock, traveling tens of thousands of miles per hour, hits Earth's atmosphere. It becomes a fireball, a plasma-hot meteor. We've argued that the center might stay cool, acting as a heat shield. But the physics of thermal sterilization are brutal. The vast majority of meteorites burn up completely. To survive entry, the rock must be large, but not too large, and hit at precisely the right shallow angle. The Goldilocks window for a survivable landing is terrifyingly small. But the most powerful counter-argument isn't about physics. It's about philosophy. It's the principle of Occam's razor, the scientific guide that states the simplest explanation is usually the right one. Panspermia, for all its narrative power, isn't actually a simpler solution. It doesn't solve the fundamental mystery of how life begins. It just passes the buck. It outsources the problem to Mars or to some other unknown planet in some other unknown star system. A skeptic would argue that we are simply trading one problem we can study, the early Earth, for an identical problem on a planet we cannot. We are, in effect, giving up on our own planet's ingenuity. We are staring at a locked door, and instead of trying to find the key, we've just decided the door must have been opened by someone from the next house over. This brings us back to our impossible timeline. Is it really impossible? Or is our timeline just a reflection of our own lack of imagination? We call it a miracle because we can't yet make life in a test tube. But our planet had the largest test tube in the solar system, its entire ocean, and hundreds of millions of years to run the experiment. Maybe 200 million years isn't a geological instant. Maybe, for chemistry, it's an eternity. Perhaps we've just been looking in the wrong place. The warm little pond at the surface was a terrible place to be, under a toxic sky and a rain of asteroids. But what about the deep, dark bottom of the ocean? Down there, protected by miles of water, are hydrothermal vents. These are volcanic fissures in the Earth's crust, gushing superheated water, rich in minerals, hydrogen, and metals. They are natural, high-energy chemical reactors. These deep-sea vents provide everything life needs. A rich soup of chemicals, a powerful energy source, and total protection from the chaos on the surface. Many biologists now believe this is the most plausible cradle for life. Here, in the dark, life could have quietly emerged, not as a gift from the sky, but as a deep, terrestrial secret. In this model, abiogenesis, life starting here, is not an improbable miracle, but an inevitable consequence of Earth's own geology. So we are left at a crossroads. On one hand, we have the tangible evidence of Murchison cosmic starter kits falling from the sky. On the other, we have the powerful logic of Occam's razor, pointing to a simpler, homegrown origin. The panspermia hypothesis is beautiful, and it may even be true. But as of today, it lacks the one thing a theory truly needs: a smoking gun. We have found Martian rocks, but we have never found a single, indisputable Martian microbe inside one. This tension, this debate between a homegrown and a delivered origin, is the real heart of the matter. It forces us to confront a question that is as scientific as it is philosophical. Is life a local phenomenon, a precious and perhaps unique accident of our own planet's chemistry? Or is the entire cosmos alive? Is the galaxy a living forest, and our world just one of many trees, all sprouted from the same ancient drifting seeds? So, after this journey, from the molten hell of the early Earth to the cold factories of interstellar space, we are left with our original question. Was our DNA a gift from the stars? We've explored two profound, competing stories. One of life as a homegrown terrestrial secret, forged in the dark, high-pressure reactors of our own deep oceans. The other of life as a cosmic refugee, an ancient microbial seed arriving on a fertile, empty world. The truth is, we do not yet know which of these narratives is correct. But perhaps, in our binary search for a simple here or there, we have missed the most important revelation of all. The debate between panspermia and abiogenesis, in the end, may not be the most important part of the story. The evidence has pointed us toward a deeper truth, one that unites both theories. We know, as a matter of scientific fact, that the alphabet of our existence is extraterrestrial. The letters of our genetic code, the nucleobases, and the building blocks of our cells, the amino acids, were not invented on Earth. We have found them like a smoking gun, sealed inside meteorites. They are cosmic, ancient, and abundant. We know, from pointing our telescopes at the dark patches between the stars, that the factories for this alphabet are the vast, cold, molecular clouds that drift through the galaxy. The universe, it seems, is not sterile. It is a chemical factory, constantly and inevitably manufacturing the raw components of life on a scale that dwarfs our comprehension. This, by itself, is a revolution in our understanding. So, was our DNA a gift? The answer, in the most fundamental sense, is yes. Perhaps not as a fully formed microbe, a deus ex machina, delivered to solve our timeline problem. The gift was the chemistry itself. The gift was the starter kit, delivered by countless comets and asteroids, which made the emergence of life, wherever it happened, not a one-in-a-trillion miracle, but a biased, chemical inevitability. In the end, it makes little difference whether that first spark ignited on Mars or on Earth. The source material is the same. The atoms that form the scaffolding of your DNA, the carbon and nitrogen, were forged in the thermonuclear heart of a star that died long before our sun was even born. You are, quite literally, made of stardust. And the molecules that make up the rungs of that DNA ladder, the complex code that separates you from a simple rock, were assembled in the cold darkness between those stars. Life, it seems, did not have to fight against the universe to exist. Life appears to be a fundamental expression of the universe. It is a property of the cosmos, not a random accident within it. This new perspective radically changes our place in the cosmos. We are not a lonely statistical fluke, clinging to a single special planet, isolated in a dead and silent void. We are a product of that void. The universe is not a passive backdrop for life. It is the active, creative engine of life. The laws of physics and chemistry seem to conspire, over billions of years, to build complexity, to turn dust into information, to make matter aware. Look at your hand again. It is not just a machine built from stardust. It is a living archive. It contains a genetic code, an unbroken thread of information, that connects you directly to the first successful replicating organism on this planet. But the connection does not stop there. It goes further back. The atoms in your hand are a loan from the Milky Way. The blueprint that guides them is written in an alphabet that was forged in interstellar clouds. You are not simply in the universe. You are the universe. You are a localized, temporary assembly of its most ancient dust, animated by its most complex chemistry. We are the cosmos finally awake. We are the consciousness of the stardust, the voice of the molecular clouds. We are the universe reflecting upon itself. And the grand, terrifying, beautiful journey we are just now beginning is not to find out if we are alone, but to finally understand what we are. We are, in the deepest sense, a gift from the stars, looking back at the stars and finally beginning to come home.